Okay, continuing our review of quantum mechanical model. First of all, I want to say a few words about these quantum numbers. So we will start in this video with the principal quantum number n. So what is the significance of n? So we can say a few things about n. The first one is that n determines the energy of the electron. So n determines the energy E sub n of the electron. So it depends on the value of n. Uh, in Bohr model, we have a relationship between the angular momentum and n. The angular momentum p theta was given as being quantized in units of h bar. So it is n times h bar, where h bar is Planck's constant h divided by 2. But later on it was found that for a given energy there are several different angular momenta possible. So if you recall that the values that L can take are 0, 1, 2 to n minus 1. So actually several angular momenta are possible for a given value of n. So this is not quite right. For the hydrogen atom, the energy levels are given by minus 13.6 electron volts divided by n square, where n is 1, 2, 3. N equals 1 is the ground state, which is the lowest possible energy state. And this 13.6 basically comes from the Bohr model, so you can see it has a dependence on mass of the electron, the charge of the electron, and permittivity of free space and h bar squared. When we have electrons with a certain n value, they are said to be in a particular shell. So electrons with a particular n value are said to form the nth shell. So these shells are named as n equals 1 is the K shell, n equals 2 is the L shell, n equals 3 is the M shell, etc. So these shells are given names K shell, L shell, and M shell, etc. So how many orbitals do we have in the nth shell? There are n square orbitals in the nth shell, and each orbital holds a maximum of 2 electrons. And they have to be with opposite spins, but we will talk about that a little bit later. So for example, when you have n equals to 1, the K shell, there is only one orbital, which is the s orbital, and that accommodates 2 electrons. If you have n equals to 2, that has 4 orbitals, and these are s, px, py, pz orbitals, and these we have seen here, px, py, pz. They can accommodate maximum of 4 times 2, 8 electrons. N equals 3 has 9 orbitals. So these are S, Px, Py, Pz, Dx, Dy, Dz, dx square minus y square dz square. And because we have 9 times 2, a maximum of 18 electrons that can be hosted. So finally, I would like to make a remark about the contribution of N to the magnetic properties of atoms. So that's basically of interest for this course. As you can see, N does not directly have any influence on the orbitals, other than so it doesn't really have a direct influence on magnetic properties, but it has an indirect influence. So we can say that while N, the principal quantum number, does not directly determine any magnetic properties, it still has an influence by controlling the orbital angular momentum quantum number and magnetic quantum number, m sub l. So remember that when we have a given n value, the allowed quantum numbers are, for orbital angular momentum, L equals 0, 1, 2, all the way up to n minus 1. And then for each L, we have a corresponding magnetic quantum number, m sub L, which ranges from minus L to plus L. So since we set the maximum limit for the orbital angular momentum quantum number L as n minus 1, so n does have an indirect influence on the magnetic properties as well. Okay, so we have a quick review of principal quantum number, which determines the energy of the electron. In the Bohr model, the angular momentum was given quantized in units of h bar as n times h bar, but then we have found out that for a given shell, we have several possible orbital angular momenta possible from 0, 1, 2 all the way up to n minus 1. So this was not accurate. The hydrogen atom energy levels are given explicitly as minus 13.6 electron volts divided by n square, where n equals 1 corresponds to the ground state. N equals 1, 2, 3 form the K shell, L shell, M shell, etc. And for each shell, we have n square orbitals in the nth shell, and each orbital holds a maximum of 2 electrons, and these are named S, P, D, and F. So sharp, principal, diffuse, and fundamental, etc. So that those are some spectroscopic labeling. And the end effect on the magnetic properties for the principal quantum number is indirect through determining the other quantum numbers, orbital angular momentum quantum number L and the magnetic quantum number m sub L.